All right, so let's start. Hello, everyone. Welcome to episode 32 of Warsaw Quantum Computing Group Meetups. Today we have great speakers from Zapata Computing, Manuel, Rudolph, and Michał Stęchły, and they will give a lecture titled ORQVIZ, Visualizing High-Dimensional Landscapes in Variational Quantum Algorithms. I'm not sure if I read this name correctly, but you can just do it in a correct way for sure. All right, so before we start, I would like to let you know that this meeting is recorded. So as usually, the video will be later available on our YouTube channel. And if you have any questions, you can just post your questions on our chat during the lecture. So we want this meeting to be interactive. If there are some urgent questions, you can also unmute yourself and just try to ask questions. And there will be also a Q&A session at the end. We would like to thank our strategic partners, Snarto and Korek, for just supporting our meetup, and our honorary partners for helping us in advertising this meetup. So now I will just stop sharing my slides. And Michał, Manuel, if you are ready, the Zoom is yours and you can start. Thanks for accepting our invitation.
Yeah, thank you for having us. Yeah, I think I'm going to start, right, Michał? So
yes.
The pronunciation, it's probably a little awkward, but we would say ORQVIZ, and it's obviously a combination of orchestra, which is the whole, it's like essentially what Zapata is working on in terms of software, cloud computing, research, like everything is brand orchestra, and VIZ standing for visualization. And yeah, so you can probably see my slides quite just fine. Okay, so as you might be aware, we released 2 weeks ago a paper and a Python library together. So the paper is called ORQVIZ, Visualizing High-Dimensional Landscapes in Variational Quantum Algorithm, and ORQVIZ being the open source Python library for visualizing high-dimensional landscapes. Now, this is so ORQVIZ gives you a toolbox, an open source toolbox. You can pip install it for a bunch of wrapper functions and also techniques which you can apply to very seamlessly and easily visualize your parameterized algorithms. Now, it doesn't have to be a quantum computing algorithm per se. It also doesn't have to be a variational quantum algorithm in terms of the variational principle of quantum mechanics, right? That you're like optimizing to approximate a ground state, right? So variational can be very in the broad sense, where any algorithm where you have parameters which vary in order to solve some task, right? So we try to find a word, like a phrase, here being variational quantum algorithms, to encompass all kinds of parameterized algorithms. I mean, we are quantum researchers, so and we provide some helper functions which are specific for quantum algorithms, but this is not limited to this, to just quantum algorithms. Now, what's the paper? The paper is a collection of the visualization techniques that you have available for ORQVIZ. We demonstrate them, we explain them on different levels of technicality, and we always show the actual visualization that you produce with the corresponding techniques from ORQVIZ. And then after some introductory section, we have case studies where we apply ORQVIZ and the visualization techniques to a range of examples, right? So we have research case studies, and we try to approach them from the visualization perspective. But I will get to what visualization is in a second. let's cycle back a little bit. Again, variational quantum algorithms isn't just variational principle. It isn't just VQ. Now, technically speaking, VQ, like variation quantum algorithms might refer to that, but we really want to be general in the case, in the sense that every kind of parameterized quantum circuit application. Now, VQAs are our attempt at making quantum computers useful as soon as possible on noisy intermediate scale quantum devices. So they usually, right, so you employ your parameterized quantum ansatz with a loss function that might be Hamiltonian energy, that might be a classical loss function, depends on your task. If you vary the parameters, you then try to solve the task. So there's a couple of theoretical guarantees, actually not too many. And so we don't actually know what's going to stick far term. However, we assume that at least some of it, and of course, much of what we learn about it will stay with us in the far term. But they are commonly treated as black boxes in the sense that you have any type of problem, and unless you are doing exactly VQE, even there's like very little inspiration of what the exact ansatz structure is. Maybe QA away if you're familiar with these terms, but it's not too important. Usually, especially for quantum machine learning, people don't think about it too much, right? It's like you have an ansatz, you have your parameterized quantum circuit, you optimize the parameters, you just look at the final outcome. You look at like, what's my loss function at the end of training? That's a black box. That's not helpful. It doesn't help us to understand how will this algorithm behave once we actually go to the number of qubits that would be intractable classically. The only reason we're doing these algorithms is because, well, eventually, like studying the algorithm, we want to eventually go to a number of qubits which we can't simulate anymore, right? And just because we have a black box algorithm that kind of works with 5 qubits, there's zero guarantees that this will at all work with 50 plus qubits. And in fact, pretty sure it won't work, right? Why? Because we haven't quite understood it. There's so many aspects, like trainability. How easy is it to navigate the loss function during training? Is your ansatz expressive enough? Then you have things like barren plateaus, which are related to like smart initialization, which usually isn't done. Also levels of noise, also which kind of loss functions you're using, that also induce barren plateaus and also have like their connection to expressivity, but like how good the solution can be. Then the actual noise of the device, that's an entirely different thing. In QML, you have stuff like data encoding. What's the best way to encode your data into a quantum circuit if you want to, for example, classify or to generate stuff? Now, that's a whole lot we don't know. And there is, of course, theoretical studies, and they are very valuable. And there's, of course, numerical studies, which are necessary. Now, there needs to be this interface between I kind of know what I'm doing because there's kind of the theory behind it, and there is and I have evidence that it works in practice. Both of these are very necessary. Otherwise, we can't play around with like 5 or 10 qubits and hope that with 60, 80, 100,000, let's say like logical qubits, it would work. Like we have no evidence that this should work. So what we need to do is not treat VQAs as black boxes, and we have to start now. Otherwise, even the simulator hardware is getting better and better. The simulator software is getting better and better, right? So we can't just lay back and simulate up to 20 qubits eventually with our GPUs and TPUs, like on a laptop, just because we can. We need to understand what we're doing right now, where there's as few as possible moving pieces, and we like layer by layer kind of extract knowledge given kind of our attempt of the VQA. And visualization is one of the tools that we really want to give onto people's hands to help open this black box that VQAs currently are, just to have another tool available to study where you don't necessarily need, you don't at all need theoretical background, and you don't need like huge over-the-top numerics. Like this is there to supplement whatever kind of research you do. Now, what's visualization for me? I would more or less easily phrase it as plotting a function of a parameter manifold. Now, yeah, this might sound a little more confusing, like a little unnecessarily confusing, but visualization has a couple of components that I want to kind of pull apart here, just so we appreciate what we're doing with ORQVIZ and in the following a little bit better. So what's the function? Now, when you think of landscape, right? So you think of kind of like, I usually think of like a mountain landscape, maybe kind of a sea landscape. When the open sea, you have like these waves and you try to navigate that, right? But the thing is, the landscape isn't the model. The model itself doesn't necessarily have a landscape. What landscape means is you have a function which you have to evaluate. The function gives you actually the like y or the z value, depending like, right? So like this like scalar dimension that you're taking the landscape of, that's the function. And so the function could be the training loss function, right? And then you have your loss landscape. But we very carefully didn't include loss in the title of the paper, because you could also scan any kind of function which receives parameters, or let's say this receives parameters and spits out a real number. So for example, you could also cross evaluate your model. So you measure a function like a value which you aren't specifically optimizing for, but which you do care about, just to see how is the model performing with respect to that. You could also plot fidelity with respect to a known state, right? So with respect, for example, to the exact known ground state of the Hamiltonian that you are trying to approximate the ground state of, right? And so you can kind of not only measure the energy, which would be the loss function usually, but you could also kind of visualize the fidelity with respect to the ground state. But you can get very creative. Anything which gives you one real number associated to a constellation of parameters can be plotted. So gradient magnitude is what's typically measured for barren plateaus, like to identify barren plateaus. How does the mean variance of the gradient kind of go down with the number of qubits? Right? But the mean of the variance is actually a single number, and that could be plotted. Like that's something like that could be the function that you're visualizing. And also much more exotic stuff, Fisher information eigenvalues, and whatever you can think, any function that takes parameters and gives you a real number would work. Now the parameter manifold, right, is the low dimensional. Sorry, I think someone's unmuted, but I will just carry on. So
I will try to mute. Okay, yeah, go on.
Yeah, thank you. So the parameter manifold, it's like a slightly complicated name, I guess, for a low dimensional kind of manifold of parameters in your high dimensional parameter space, right? So if you have 10 parameters, you have a 10-dimensional space where every parameter vector is a point, right? And so, but you can't visualize, you can't look at 10 dimensions, you can't attempt to do that. And especially if from every point you evaluate your function, it's already like 11-dimensional. And so a parameter manifold should really be a very low dimensional parameter manifold, 1D, 2D, kind of that sits, kind of that slices something, your high dimensional parameter, like your high dimensional parameter space. And now the question is, the ORQVIZ assists you in that. How do you choose the parameter manifold to evaluate the function of? So you could, right? So you could, starting from any point, just go in random directions to kind of scan along those lines. You could interpolate between points. We will see that in a second what that all means. And most specifically, we provide kind of three main algorithms, let's say, right? That gives you, they give you specific, that kind of extract meaningful parameter manifolds given the function that you want to scan, or given kind of a collection of parameter vectors. So again, we'll see that in a minute. So these three points over here are kind of the algorithmic part of ORQVIZ that help you be smart about what you visualize. All the rest is essentially helper functions, wrapper functions that make it super easy to visualize. And just to come to the plotting part, of course, it's a question, okay, 1D, 2D, 3D, what do I want to plot, and how do I plot it? There is a lot of defaults in ORQVIZ that makes it all super easy. You don't have to go beyond that. So I don't think we have to worry too much about this. So again, this is how I understand visualization. We're plotting a function of a parameter manifold. Now, what's the parameter manifold? Just to have like a more concrete picture. Let's say this was a high dimensional space. I just have 3 dimensions here, but in the following examples, I will like vary many dimensions. I specifically like denote this as, right? So let's say I have a high dimensional parameter space, and every point in here represents a vector with the entries corresponding to each individual parameter, right? And so what could a parameter manifold look like? It could look like this, right? It's kind of a plane in this high dimensional space. The plane would be 2D manifold, right? And it doesn't matter how high dimensional the entire parameter space is. The plane is 2D, and then you can kind of discretize this plane in the sense that every kind of continuous point on this plane you can discretize, and each point gives you a certain parameter vector. And so what you do now is you evaluate every point on this plane with your function, right? You feed those parameters into your function, and then you, for example, color this plane in the result of the function evaluation, right? And so this is kind of a tilted projection. If we actually looked in ORQVIZ, we would see a 2D plot that actually carries these colors. Right? So it's a column map. So yeah, again, now the question: how do we choose this plane? So this is like a random point, and we just need 2 direction vectors which span this 2D plane. Right? So the origin and the direction vectors uniquely define what's the parameter manifold. Now, these are kind of random, but we could, for example, interpolate between 2 points, or we apply one of these 3 techniques, which I'm going to explain now. So I guess the simplest one, but I think it's also the most beautiful. Okay, Michał has a question.
Yeah, no, I just wanted to mention, if anyone has any questions, then like please just ask.
Please, yes.
As we talk, because we definitely don't want people to get confused early on and then just lose them.
Yeah. Okay, so how do we choose this? The simplest one, and I think in a way, the most beautiful one, because it's so simple, and one that has proven to be very, very useful in practice, is principal component analysis, PCA. So I'm not sure if you are familiar with principal component analysis, PCA, but PCA is a linear algorithm for dimensionality reduction. So what does linear mean? And what does dimensionality reduction mean? Let's look at this in an example. Right. So I have kind of sketched here what the shadow would be of a parameter trajectory. Right. So this could be like starting here from optimization, and then kind of the optimization algorithm in parameter space ends up here. Right. So this would be like our solution. And so if we tried to now find a 2D plane to kind of visualize and maybe to project our parameters on top, how would we do that? PCA gives us in one way. So very naively, we could think, okay, we could project kind of the trajectory in this θ1, θ2 plane. And then it would the shadow would look like this. Or we could project in the θ2, θ3 plane, then the shadow would look like this. But this also doesn't, right? So essentially meaning we would choose our plane to be spanned by the actual unit vectors of the parameter space. But that's not optimal. That's really not optimal. What is optimal is to choose the kind of plane to be spanned by the so-called by the first two PCA components. So the PCA components are essentially the output of the PCA algorithm. They kind of put the spanning vectors in the dimension which explains the most variance of your data points, right? So if I have this slice over here that kind of goes through my data points, if I projected my data points on top, it would look like this, which is more spread out than down here or up here. So spread out means you lose the least information, but you're still just casting a shadow. But now it's from the top, now it's on the side. Now it's like actually from the direction that's calculated by PCA, right? And so essentially from a parameter trajectory, applying PCA, we receive pretty much for free our 2D plane that's centered around the mean of the point collection. And now again, can evaluate the function, in this case, actually loss landscape. And this is the plot we would get. Right? The trajectory I did I did post-process, but the plot is actually one from ORQVIZ. So that's PCA. You need a collection of points to give you a direction vector, two direction vectors, and then you instantly have a highly informed direction to perform the scanning of the function. That's super flexible. And for example, you could also apply PCA on a collection of points which don't come from a single trajectory, but kind of are, for example, you could do PCA on previously found good solutions. That would be another attempt. The thing is, these points need to be kind of low dimensional in the first place, right? Like how the parameters are connected needs to be a lower dimensional space already compared to the high dimensional space. Otherwise, this kind of casting shadow will be very lossful. Like we'll have a lot of loss, like approximation error. But PCA is great. So another way that we can get
I have a question.
Yes, hello.
Related to previous slides, I don't understand it much, but I just have a question. So if I just fix θ3 naively, right, then also I'll get a plane, right?
Yes.
And then what is the difference? I mean, benefit of using PCA? Because I mean, first of all, I'm not able to visualize how it is applied here and what is the benefit of it. So if you can describe a little bit, that would be very nice.
No, that's a great question. So there's two things we want to maximize essentially. So we want to maximize the information, like the meaning of the direction we scan, of the plane that we scan, and usually we also would like that we can project this kind of these points that are informed, right? They come from optimization. They have interacted with the loss landscape. We would like to project them on top, right? And both of that is actually like PCA is like optimal in the sense that there is no linear transformation that can give you that with less error, right? So it chooses two directions where you can project the trajectory on top with the least approximation error, and you can then also like scan the landscape behind to scan the landscape which is most representative of the actual kind of optimization trajectory, right? So you could there's no linear plane which you can scan that represents the loss landscape that of the optimization trajectory better than with PCA.
Okay, so it basically tells you the direction where you should optimize, or choose a plane.
Yes, so optimization, right? So it's like posteriori after training, or like after. You don't have to train to apply PCA, but having an optimization trajectory, for example, from gradient descent, is kind of a local collection of points, right? And they all kind of have correlation with one another, and so PCA will be very will not lose a lot of information because the trajectory is. We have seen that in we have soft evidence that the first two components, right? So if you have like this picture here, explain more than 80% of the variance, like 100-dimensional even models. So it's surprisingly low-dimensional. PCA is very good in extracting that.
Okay. Also, I wanted to mention that actually PCA it's like just like a piece of linear algebra. There's like no magic there. It's like relatively simple algorithm. So if you just like look it up online, you should be able to understand how it works without too much trouble. It's pretty straightforward.
Okay, thanks. No, I have not seen it being applied after you do the minimization. So it was something.
Yeah, exactly. And so evaluating this function, right? So going from here to going here, this is of course you need to call your loss function. If your loss function has a quantum simulation, that is expensive depending on the application.
Yeah, sure.
Just applying PCA is actually free, right? Like that takes like microseconds, and so just for free you can just see how much, like how low dimensional your optimization trajectory is, which is a very soft proxy for how complicated the landscape is to navigate.
Okay, thank you.
Welcome. Thank you for the question. That was very, very necessary to be asked.
Thanks.
Great. Anyone else have a question? Otherwise, we can just go to the next technique to choose directions. Right. So, and that is Hessians. So Hessians is the Hessian of a function is the matrix of second partial derivatives. Right. So it's how much the gradient changes as you like with a certain perturbation. Right. So it's the curvature. Right. So a parabola has it's like the second partial derivative of a parabola is just 2. Right, like x squared, second derivative being 2, right? So that's the curvature, and the Hessian matrix has each entry being the combination of partial derivatives with respect to the parameters. And if we actually apply that to kind of the final point of our optimization, what we actually expect is to see something like this. So this would be a 4-dimensional model, and all eigenvalues, right? So here's like the magnitude of the eigenvalue of the Hessian, and this is just like which eigenvalue. We expect it to be all non-negative at a minimum. So that's kind of the definition of a minimum, is that you have no negative eigenvalues. That means the Hessian is locally positive semi-definite. It's convex. Now that's just right exactly at the minimum. But for example, in this case, we have 4 eigenvalues 2 around 0.5, and 2 around 1.5. Now, what do we do with that? So this is something that people already do. That's kind of like quantitative, right? That's like numerical analysis. Now, but you can use those eigenvalues and the associated eigenvectors to visualize. So to choose your directions. So for example, the first 2 eigenvectors, this here 0 and the 1 eigenvector, let's assume that they point in these directions and they are orthogonal to each other. Right? And then we have also the green and the red one. We can actually choose those direction vectors and evaluate, for example, the loss, to evaluate the function if we scan along these eigenvectors, right? So this blue curve here is essentially, we evaluate the loss on this line, right? So here is like the 0 eigenvector direction, then here would be like plus pi, and here would be minus pi. Right? And so the Hessian essentially gives us informed directions in the sense that in these directions, the curvature is maximal independent from all the other directions. That's what the eigenvectors indicate. And on top of that, we can plot that in the same plot. So even though this is 4-dimensional like parameter space, we can plot that in one 1D plot and evaluate the loss. And we can see, well, these 2 eigenvectors, what that actually means is that the loss is increasing faster, right? And so this is also what the scans indicate. And these 2 eigenvectors that are kind of lower, they indicate, not always, but we can see it in the scan now, that these eigenvectors actually indicate that there's kind of a flat area around my found local minimum that this wasn't obviously showing me. Now, if it was 0, like if the smallest eigenvalue was 0, like there was a bunch of 0 eigenvalues, there some people would say, okay, this is like flat, it's like exactly flat. But these shallow areas, this isn't something that eigenvalues don't resolve. And now we can also use these eigenvectors to span a plane, right? So we can take this plane that is defined by these 2 eigenvectors, and just like in PCA, we kind of now choose a 2D plane space which has the lowest curvature in like locally at least. And we can do the same with the higher eigenvalues and their associated eigenvectors. We can now choose a scan which we know has locally the highest curvature, which contains it, right? And so the actual landscape kind of at this red point is kind of a mix of all of these scans, of course, right? Because we're only looking at 2 directions at the same time, but then there's of course many of them. And right, and so that's Hessians. And just to get to a super exciting algorithm, and then hand it off to Michał to show you examples of that, of ORQVIZ. It's the natural elastic band. The natural elastic band is actually an algorithm which makes me really excited because it's so pleasing. So let's say you have 2 points in parameter space and they both are minima, right? You could now interpolate between them. This is what I meant at the beginning. Choose your like scan direction by interpolation. So you have here on the y-axis the loss as you move from one point to the other point, right? And so again, a line and a plane in parameter space is totally disconnected from what you evaluated, right? So this is completely linear, but of course the loss you evaluate isn't linear. It's like whatever your function is on each point, right? And so if I could actually also make a 2D interpolation scan, ORQVIZ also provides that, right? So, okay, that's interesting. Now we see kind of around these points, you have these high curvature rings that we also saw in the Hessian, right? And these minima seem to be disconnected in the sense that you need to like go over this kind of loss hill to get to the other minimum. But what we have to realize is that we're just forcefully slicing through the space, right? So it's only informed in the sense that the beginning and end point are informed because they are the result of optimization, but then we're just slicing through the space in hopes to actually find meaning, right? But that's actually not always the best thing you can do, right? So you have to realize that everywhere on this scan, there is a force gradient. There's a gradient of the loss, and if we, right, and so this is something that if you were optimizing, you would actually feel, right? You would kind of fall down the slope of the loss gradient, whereas a scan doesn't respect that. A scan plane doesn't kind of slope with the loss, and so the natural elastic band comes in that you discretize this line, because obviously you're working with computers, you can't just like well, I guess you could, but you essentially you simulate discretely how this kind of connection vector, if you let it relax, you have like kind of this elastic kind of model of the connection, let it relax in the loss field, and then you actually observe not only that your loss, for example, is like super low, and these minima were in fact connected by low loss, but you can then apply a PCA scan on this path. So this is to the question before. So this is essentially what, I don't know, was it, what the person was asking. This is an uninformed direction. This works. But if you just tilted the plane in a different angle, right? So only the second direction is different, essentially. Now suddenly it looks like this, right? You just need to find the best second direction, right? And the natural elastic band is a way to find the lowest loss barrier between 2 points, like the saddle point. And this can perfectly be combined with PCA to kind of demonstrate where this elastic band is going and what the loss landscape below it looks like. Right. So this is this was essentially a demonstration of what you can do with ORQVIZ, with schematic images, but all of these kind of colored plots and data plots were actually generated with ORQVIZ. And we can go into like detail of like scientific outcomes, like results we had in our paper, where we like apply these techniques to kind of case studies of research. But I think it's good to hear from Michał how you would actually use this open source Python library, ORQVIZ.
So
yeah,
please go ahead.
No. Go.
Yeah. So basically, PCA would be useful to find this particular direction and then use these techniques to analyze, so that you can see how the loss is changing in a landscape, right?
So you would apply first the natural elastic band algorithm to essentially go from a linear path that has this kind of behavior on it, to a non-linear path which has this loss like behavior on it. And then you can afterwards kind of demonstrate the shape of the path by applying PCA in a PCA scan. Okay. So this algorithm is disconnected from PCA.
Oh, okay. But the results results should match actually, right then, right? Because it will find a direction, the PCA would find a direction where we can see exactly similar kind of loss landscape, right?
Yes, so PCA would find the linear plane that is most representative for the actual path.
Yeah.
Right, and then we would scan the landscape behind it, I will always say, to see like an approximation of what the landscape looks like on which the path is kind of lying.
And which of these are faster? At least comparing this elastic band and PCA. Which one?
Yeah, PCA is faster.
Okay.
But also it's worth noting that when it comes to speed, it's actually like, at least for the quantum circuits, usually the bottleneck is not how fast the algorithm for like performing this operation is. The most costly thing is like evaluating the cost function at any given point.
Yes, yes.
Because you have to simulate the whole circuit and so on. So actually,
it would be cost rather than being fast. Yeah.
Yes.
So
yes.
which one is more costlier? Suppose, I mean.
So like for notched elastic band, you actually have to go through several iterations of like evaluating cost function at different points. So it's pretty costly. And for PCA, you basically take a vector of points and their values and run some linear algebra on that, right? So
well, I mean, it's yeah. So they're both kind of loss function evaluations, but the all visualization techniques are like nothing here is for free unless you just apply PCA without a scale, right? Nothing's for free, but we are right. So these are techniques to kind of understand what you're doing, and I think right, and even with like 4, 6, 8, 10 qubits, which you can simulate in seconds, we have a lot to uncover, and we can run these algorithms on a laptop in like seconds, minutes, hours, but then we learn something from it, right? So this isn't something you would run on actual quantum hardware. This is like these are tools to kind of step by step understand what we're doing, and all of this is connected to, of course, like loss function evaluation and simulation cost, natural elastic band more so because it requires only functional evaluation but gradient evaluations, right? And so that's in general much more costly. But yeah, so with like 6 or 8 qubits, these scans you can do in a couple of seconds, depending on like how fast your simulator.
Okay. Thank you.
Okay.
Thanks.
So okay, let me show my screen, Manuel. I will just find the right slide. Okay, so, oh no, I clicked play on start. Sorry. Here we are. So two more things I wanted to mention. One is that we actually haven't invented these techniques ourselves. We just kind of packaged them nicely, implemented them, and applied them to quantum circuits. And the other thing is that these are all just like tools, and like some of these tools work well with one another. Some you shouldn't use them kind of at the same time, and so on. So there's like a lot of if you want to like play with that or use that in your research, there are some like judgment calls, like actually, you know, which method you want to use for this problem or for that problem, which makes sense, which is too costly, which is not. So there is some thinking you need to do around this. But I wanted to tell you about the software side of this, small package, and just like what kind of we had in our minds before, like while doing this. So there are a couple of issues with existing solutions, and by existing solutions I mean mostly using Matplotlib to just do your visualizations. And we are using Matplotlib under the hood. But what people usually do when they're doing some visualization is they're just like writing some scripts that they work for this particular project, and then when they start the next project, they write new scripts or reuse the old ones. But there's always like something specific about your, like this specific problem that you need to write in from scratch. And the problem with Matplotlib is that this is like the part, like in reinventing the wheel for every project, basically. But the problem is that there are like a lot of options, and it's just sometimes overwhelming of like what you can do with Matplotlib and whether you should use this like PC color mesh or ImShow or maybe something else, or scatter plot to actually show this loss landscapes. So this is like one of the issues that we kind of are facing. Another thing is that a lot of these visualization techniques involve some linear algebra, and while you can think that in principle taking a vector or like a matrix of points and transforming it to some other points, or is just like multiplying a bunch of vectors, together, it turns out it's usually surprisingly tricky to actually do it properly. And you end up with some issues like, oh, I forgot to normalize my vector. And like, actually, if I just like multiply by like unnormalized vector, I get total trash and things like this. So at least from my experience and Manuel's, like whenever you try to do these things, you run into some of these issues. And the last one is there's with Matplotlib, there are a lot of those like super tiny details that are really annoying. Like depending on which method you use for visualizing like points on a grid, they set, for example, the coordinates of the points either in the bottom of the pixel or lower left corner of the pixel, or like they might have different orientation. So some tell you that the 0.00 is like bottom left corner, but in some others it's like top left corner, and so on and so on. So it's, you know, it's like always a hassle to actually make it work and like make sure it works the way you wanted it to work, and so on. So these are like some problems that we were facing, probably are still facing with working just directly with Matplotlib. And what we wanted to create was a library that's like easy to use. So how we try to achieve that? So first we try to create relatively simple interface where, you know, that doesn't overwhelm you with the, you know, amount of options, that allows you to actually understand what, you know, given method is doing. And also that provides you with some good defaults for starters, so that you don't need to think about, you know, all the details. Just start going, exploring it, and then maybe, you know, add whatever you need, you find necessary. Another thing is that often with those visualization, like in different research projects, is that people tend to mix the visualization logic and the actual execution logic. And this might not be a big problem if you are running it on your laptop and, you know, like there's not that much compute going on. But actually, if you want to run part of the computations on a cluster because you need to simulate pretty big circuits, or whatever, then it actually starts getting more tricky, and you actually want to disentangle these two, like execution logic and visualization logic. So what we did, we tried to separate these as much as possible, and we also wanted to create some data structures that are reusable for different purposes, and also allow you to like are kind of separated, right? So you don't need to create a new data structure for like every single thing you're doing, but you have data structures like contain enough information for your purposes. And the way we, like, I think that's the last one is actually the most important one here. Well, you can't do that for visualization library in general, but if you know what you're focusing on, and in our case, we just want to focus on visualization techniques for cost landscapes, right? Then we can make some choices that just allow us to meet these other criteria, because we are dealing with only like one class of the problem, right? So it's not general purpose visualization method, like visualization for library for everything. It's just for cost landscapes. And therefore, we try to make it as easy as possible to, you know, use it with cost landscapes. So if you go to the repo and start playing with that, there are basically two kind of good things to know before we start. And I'll show that you in a moment in the code. But first, the loss function or the cost function, or whatever else you might want to call that, we use loss functions that are taking just a vector of parameters as input. So sometimes cost functions like actually take more things. In such case, you need to Well, play around with that a little bit and find a way to actually rewrite it in a way that it actually takes only a parameter vector, which is totally doable in Python. And the second thing are 2D scans, and I'll be focusing on, like, from all the methods that like Manuel showed, I'll be focusing mostly on just like 2D, like starting from 2D scans, because they're like the easiest to understand and the easiest to use. And regarding the data structures, well, here is an example, right? So this like scan 2D result is just a data structure which contains this information. So like the parameters, the directions in which this manifold or the slice is, like, you know, where it is, the values for the parameters, and also like the origin point of the of this scan. And we have the function perform 2D scan, which takes a lot of different things, but it requires only origin and the loss function. And I will show you how it looks like right now. So now let's software for real.
Yeah, while Michał is like setting up the example, I want you to like specify that these outputs of ours, like perform 2D scan functions, they contain everything necessary to reproduce the like initial, like what you actually scanned, right? So you only have to save one thing, and you know like what the origin was, what directions you scanned, and what the exact parameters were that you evaluated, what the exact losses were. It doesn't just, right? It's not just like saving a JPEG or like a PNG or PDF of the final plot, just saving the raw data, but it's all like in one point. You don't have to like think anymore about it.
Yeah, because like for the issue that we encountered was where you are running some scans and it's super cool, but then after running a lot of them and looking at the plots, you realize, oh, but like I actually haven't saved the directions where the scans were created, and like, oh, I actually have to run it from the beginning because I haven't stored this information. So we try to kind of gather all the necessary information in one place. Okay, so we start from you can like just like pip install ORQVIZ, and I did that before. So I imported NumPy because you always import NumPy, and just two basic methods: perform 2D scan and plot 2D scan result. And let's start from some super simple loss function, and the one I'm starting is just this one. So return NumPy sum of params squared, right? So basically a quadratic function. That's pretty simple. We know what to expect from this guy, right? So we need to say what the origin is. So let's say we are doing this in 2 dimensions. So origin is just like 2 zeros. And now we can perform 2D scan. So scan results, perform 2D scan of origin and the loss function, right? Okay, and we have this scan results object. So let's take a look how it looks like. Okay, so right here, you know, we are plotting the loss landscape for this particular function. And as you can see, it's not very surprising. There is like 0 at the bottom, like at the center. It's centered around also like 0, 0 point. And it looked like just like what you would expect from a parabola. But actually, one thing we can do is we can increase the resolution to just get a
in the scan form scan.
Oh yeah, thank you. I was surprised. Oh yeah, so now we need to redo the scan, right? And after we redo the scan, we can plot it. And as you can see, we are just like getting the same picture with better resolution, which is nice. We can also specify a number of steps for the y direction if, you know, for whatever reason we want them to be different, but usually we want both of them to be the same. So we just can specify one. And okay, this is what we're expecting, but maybe there is something weird going on with this function outside of this like scope -1 to 1 that we have here by default. So let's change this from, I don't know, -10 to 10. Right? How does it look like? Well, not very complicated function, so it doesn't look very complicated. However, you might have noticed that actually the values here change, right? Because now we are at 200s and we were at 2. Okay, so maybe that function was a little bit simple. So let's try something more complicated. So let's do the following. Let's try some sinus and some cosinus. I don't know, this might be squared. And okay, let's see what we get, right? Okay, we are getting something that looks like this. So a nice periodic landscape. But actually, let's add something more to make it a little bit more interesting. So we can do this, right? So we have some function of like sines and cosines, right? And then we just add this kind of linear term, right? That will kind of tilt the values of the function. Okay, so we got it, and that's nice. What happens if we just increase the number of dimensions? Well, the loss function will, like, this long function is defined in a way that it will take how many dimensions we want it to take. So it shouldn't be an issue. And we can just increase this, plot something, well, and we see, we got some slice. Like how the directions have been chosen? Well, by default, they are chosen randomly. So if we run it a couple of times, then we actually get different landscapes every time, right? Because they are always around the same origin, but always in like different random directions. So in order to get some control over, to get some control over where the directions, like what directions we are using, we can import the following: geometric import get random vector and get random orthogonal. Okay, so these are just like some helpers we created, right, for generating these. Okay, so let's just do it like this. Say we have 10 up, and now with this get random orthonormal vector, we can create another one, which is, well, orthonormal to the first one. So we have two. Oh, sorry. So we have two vectors that are, orthogonal to each other. We can check it by, right? It's basically 0. So now we can actually repeat the scans, but just specifying the directions. So if we do direction X is direction X, direction Y is direction Y, we got like some landscape, but now if we actually rerun it a couple of times, we are getting the same results every single time. Okay, so that's kind of, I would say, like basic functionality. Another thing is, as I mentioned, like the scan results object itself has a couple of different things. So in particular, it has the params grid, which is basically the values of the kind of parameter vector at each point that we looked. So params grid, right? So if we take a look at the shape, it's like 100 by 100 because we have this like matrix is like 100 by 100 specified by those steps. Oh, sorry, actually these steps, right? And then like it contains like parameter vector of length 10 for each of these points. And then similarly, if we go like values, we have 100 scalars, and we also store the same directions that we used. Okay, so one more like nice utility function that is actually pretty useful is like from utils import save this object and load this object, and you can basically just like take this scan results, and if you have, you want to run it on a cluster or AWS or whatever, you can just save them there and send to your local machine so that you can analyze this or just like store them for later, right? So my file and it works, you can load it. That basically gives you the same thing. And the last thing from this kind of basic stuff is that actually under the hood, like you don't have as you don't have as many options as you have in Matplotlib, but under the hood, I think, yeah, if we look at what we are passing here, sorry, not this one, the visualization one. Oh, what's happening? Okay, if we actually look at what are the arguments, so we are passing the scan results, but we can also pass like some figure or ax from Matplotlib, and also like different plot keyword arguments that we want to use for the underlying PLT p-color mesh. An example for that is here, and I would just like copy paste because there's just like too much for me to type. So we set, two directions, and then we perform 3 2D scans, and they are all in the same directions, right? But each of them is for a different scope, so we can like zoom out and see how the landscape is changing depending like where we look from. And we want to run it for, in a subplot, so basically have 3 plots next to each other. This line is only to make it pretty. Now there's like another nice utility of just like changing the ticks, on the axis to multiples of pi, which is useful when we are analyzing NF like sine, cosine, like trigonometrical functions. And then we can run it, right? So we need to pass it to like have it in a specific place. And as an example, I just like decided if you don't like these colors, you can use rainbow colors, which is just like great choice for visualization. As you can see, okay, I forgot to import Matplotlib, classic. So import Matplotlib pyplot as PLT. And as you can see, if we look at the cost function, like in a close-up, it looks something like this. Then, but like if we zoom out, we see that actually this function in like plus minus 2 pi and something looks like this. But like if we zoom out even more, we see that there is this like actually some kind of gradient going on, right? That comes from this term. So we see that like if we look from far away, like this starts to kind of dominate the landscape a little bit. And if we run it again, we just get from the same thing, but basically in different directions, right? Because we are getting random directions here. Okay, so that's, I would say, like a basic overview and like how you can use ORQVIZ. One more thing that before getting to actually quantum circuits, I wanted to make this point that you can use it not only for mathematical functions or quantum circuits, but anything that given the parameters gives you back a vector, a scalar. So I just tried to, and this is like super hacky, so sorry for that. But I just wanted to take some neural network and plot the loss landscape of a neural network. And with this neural net, I just like used some NLP regressor from sklearn, which I just created like some synthetic data set for that. So basically, if we run this regressor and just get the machine learning model, it does like some prediction. I don't really care. I created those like small util functions. So the problem is that like the model, the way the model actually stores the values is not in one huge parameter vector. It actually has it in like a couple of arrays that make more sense from the perspective of the neural network. But we can like always just like concatenate these and have them. So what we can do is we can just take this like pretty long parameter vector from this particular machine learning model that defines how it behaves, and we'll just like see how the loss landscape looks for this if we just like not try training the network, but just by hand change the parameters. So here is the thing that I mentioned, that actually loss function usually like might require more stuff than just params, right? Because in this case, loss function is actually dependent on the model that we use. So, well, what I did is I just defined like this loss function that has the model we defined before as a global variable, which is not a good practice in general, but like works for this demo. And we can define this, and then actually you can just like run ORQVIZ to get like two vectors, and just like see how the loss landscape looks like for this particular model. And it's taking a little bit to run, but I don't know, like it looks like this in these directions, and look like this in like some other directions. And basically you can just go and explore. But apparently for this data set, it doesn't look like it's particularly complicated thing to optimize, right? Because it looks very smooth. So we can learn something about this. Okay, so now I would like to show you how to use that with the quantum circuits. Unless any questions, like always, feel free to ask. But what we have a couple of examples. So when you go to the repo, I just recommend like checking out all of them. Like Sombrero is really nice one. Advanced one shows basically all the features that we have in ORQVIZ. So if you want to dive deeper, this is a good place. But we also have tutorials for different kind of main programming languages. So like Cirq, Pennyline, Qiskit, and of course our libraries as well, which are mostly open source. So you can choose your favorite and just like start playing with that. Yes, Karim?
Yes, it looks there's a question from Karim. Yes, Karim, go on. You can unmute yourself.
Hi, can you hear me?
Yes, yes, we can hear you.
Okay, well, first of all, thanks a lot for this great tutorial and this great talk. Second is, can we use this package with Qiskit and Pennyline, for example? Can we combine it with any quantum software?
Yeah, I mean, you just need to define the cost function in the way you want. So we have example with Pennyline. And I will show you.
Completely agnostic. So you write, so whatever you write as your code is completely up to you. Our examples actually cover Cirq, Qiskit, Pennyline, and also our orchestra framework. And all of that, like those 4 notebooks have the same example, and the plots are all exactly the same. The only thing that changes is like how you write loss function, because that depends on your research, right? Like on what you're actually implementing. But ORQVIZ is just a helper.
Okay, another question. Can we specify like certain types of 3 parameters? Like, for example, when or during studying pairing plateaus, we would like to focus on some parameters that we think that it might affect the shape of the landscape or of the loss function itself. So can we define some sort of like a specific variational parameters, and then plot the landscape against those specific parameters instead of the whole space itself?
Sure. I mean, it just like depends how you want, like on a specific case, how you want to implement that. But for example, you might want to, like you can put that in the loss function, right? So maybe you have these parameters, but you actually want to always like have something like this. You want to like, you know that like always the first 2 dimensions should be 0 because that's just like how you defined it. So you can do it. I think syntax would be something like this. And params, right? So, well, it's something different, or maybe hstack, right? So I just like fixed 2 first parameters to 0. And the rest are the ones that you might want to play with, or you might want to actually have some transformation of the parameters. So I don't know, like add some bias always. So that's like whatever. It will as long as you provide the loss function, which takes a vector of parameters, you can do whatever you want. And like
this is great. This is very enlightening. Thank you so much.
And yeah, also Manuel pointed out, like you can also do that with vectors, right? So maybe you want to scan always, actually don't do that, but you just might want to construct your vectors like directions in a way that like they always have, 0, 0, 1, and then other parameters. So you can definitely do that. So let's see how you can actually use some of that with Circ. So, well, importing stuff, that's simple. Here we just define some Hamiltonian that describes like hydrogen molecule. And here's like some code for circuit. It basically is a circuit with like one X gate, then a layer of Ry, and then C naught Ry, C naught Ry, C naught Ry for like whatever the number of entangling layers you want. So how we calculate the energy? Well, we take the circuit, we calculate the wave function, state vector, and then we use this function from Open Fermion that like for this qubit operator, we calculate the expectation values and we get some energy and we just use this energy, right? So this is the place that this part is like framework dependent because you are doing it differently in Penelane, for example, right? Where you have, you just use like this X val cost with, particular things. Or with Qiskit, I think you just define this like this, right? So you do some linear algebra or whatever. That's up to you. Like from this point on, it's like basically exactly the same for every single framework. So as you can see, this guy takes parameters and number of entangled layers. So again, we need to actually just provide something that takes parameters. So we created this like lambda function here. And what's the energy? That's the energy. How the circuit looks like? Well, like this for 0 layer. This one is for 2 layer, for 1 layer of entanglers. And what we can do now in practice is, if we just like optimize the circuit, right? It's like custom implementation of super simple gradient descent. It goes to this value, right? So we have that much of a gap between the exact ground state and the actual ground state. This is for like this circuit without any entanglers. And what we can do is we can actually see what's the linear interpolation between those 2 points, right? So we see that we're on this path, we're just getting here to the minimum and here we are done. So, okay, this like tells us something about the landscape. If we take a look at the 2D landscape, we can again perform the 2D scan and we can see, oh yeah, that like looks like a well-behaved landscape, right? Maybe if we look further away, it will look worse. Well, we can also kind of change that and like see like zoom what happens if you zoom out. But then we can take a PCA, and basically here are a couple of PCA, utility functions. So first we just like for the parameter trajectory. So parameter trajectory in this case is just basically like a list of points, right? So this was the first point on the trajectory. This is the last point on the trajectory, right? And we can just perform PCA on this list of points, and then we can perform, well, we call it like PCA scan. This is basically a 2D scan, but it takes first to it like takes the direction guided on the results of PCA, right? So, okay, if we do that, it runs for a moment, and then we get this picture. Right? So as you can see, this is what Manuel mentioned, that this particular trajectory, it's kind of pretty linear, right? And therefore, like this direction here explains almost the whole variance, because there's like just so little happening in this direction, right? So we can align those align directions of the plot in such way, the axis, that it covers. It has minimal variance in different dimensions. So if we take a look from further away, as you can see, well, we see it's actually periodic, and there might be, it's not that we are stuck in some local minimum. It seems that there are like a lot of local minima. So if we add another layer to the circuit, which we just do kind of, say that here we just say, let's add one more entanglement layer to this calculate energy function. And we have like second one for calculating gradients. We optimize it again. We get much better, we get much better result. And basically now we can, but now we have 4 parameters. So it gets more interesting to actually visualize how it works with more parameters. So 5 seconds roughly. And we can see how the optimization looks in this case. So in this case, you see that actually like gets from here to this valley, and then in this valley it actually goes to the minimum, right? So here it like follows the gradient this way. If we zoom out a little bit, we see that this is just like one of the many local minima that are here in this landscape, which might be bothering us because we don't know if this local minimum is like better than the others, or whether there are like some other local minima that behave differently. So we can now get to the Hessians and actually calculate. I'm just like trying to go quickly over that on an example. But if we calculate, we are getting basically the similar plots to what Manuel showed before, right? So we can now choose those directions where the loss is actually changing kind of the least, to see how the landscape looks like. And we see that this is what basically what Manuel showed before, right? That we see that in some directions it looks like there is some, I would say, like pretty big minimum, right, with some other valleys going out of it. And here it looks like totally local minimum, not connected to anything. So by choosing the right vectors, it allows us to see it from different perspectives. And then we can do even more stuff, but I just don't want to get like we're running out of time anyway, so don't want to get too much into that. But in this example, you can see actually how to create this chain, like use this notch elastic band, like align your trajectory in the minimum. So I guess that's like what I wanted to show you software-wise. There is like way more stuff in here if you're interested. And if there are any questions, please ask questions. If not, Manuel has some other stuff to show you regarding the research we did actually with these libraries. So.
All right. Okay. I don't see any questions now on chat, so let's maybe wait. If some people would like to ask something. If not, then I think we can go on. So if you have, so Manuel, if you have some additional materials to present, then I think we can go on. We still have some time, so.
Yeah, I think I will. So right in our paper, you have seen all these kind of toy models that we also have in so either a classical loss function or this kind of hydrogen molecule ground state search. All of those are in the repo, like in the GitHub repo of ORQVIZ. And in the paper, you actually find kind of non-toy examples, right? So like we had four. So we had four. Yeah. So this is our paper again. You have the archive down here. This again was a very recent paper, and we have 4 stories, kind of 4 research topics that we're trying to tackle with, like from the perspective of visualizing the landscapes. Now, if that's like loss or any other values, that depends. And so what we wanted to show is it really, right? So these are tools, but they rarely just tell you a solution. Like they don't like give you like wisdom, right? They aren't like a proof of some theory and it's like, okay, now I know it's true, right? They are a tool. And so you have to first frame your kind of research. You have to write the code that actually runs the simulation or actually like applies the parameterized model. And then you have to have an hypothesis, or you're just exploring, that's also fine. But usually you have kind of an algorithm that you're studying, usually some kind of more niche application of that algorithm that you're studying. And these four cases where kind of the most varied kind of application of kind of 4 topics we could kind of come up with that could be nicely approached from a visualizations perspective. And I want to mostly highlight one that actually goes beyond any specific algorithm, which is more like a feature, just like barren plateaus, like the other audience member was asking, right? So you can study specific algorithms or kind of a phenomenon across algorithms. And I think that's the only thing I will cover in this talk, because we're kind of running out of time, but we have like 32-page paper with a lot of plots, and we hoped to write everything so that it's like very educational and very clear, because that's what we wanted to like transfer, right? We wanted to transfer kind of experience and our understanding of this topic. So I hope you find this interesting. Right, and so what I wanted to show is so what it actually means to have stochastic optimization and what it means to have noise in your loss evaluation. And now here specifically, the noise will come from having finitely many measurements. So here we have a quantum generative model. It doesn't matter too much what it is exactly. It is a quantum circuit with a loss function. And we're trying 2 different optimizers, SPSA, that's stochastic gradient, and a genetic evolutionary algorithm. And both of them receive different number of measurements to evaluate their loss function. This is with 4 qubits. And so we see, first of all, we see different behavior, right? We see the stochastic gradient doesn't actually care too much about the noise induced by the finite measurements, probably because it has stochasticity in it by itself, right? So the stochasticity of the gradient evaluation is higher than that of the noise, so it doesn't matter too much. Whereas the evolutionary algorithm actually suffers a lot with less samples, but it's very good with the exact wave function. Now, this is probably usually kind of a plot you would kind of put in your paper or something. If you have your specific research topic, you have an hypothesis, and here's kind of the numerical study to it. But now I want to like approach this from the visualization perspective, right? And so here we actually see the actual trajectories on a PCA scan that give this data, right? So here we have the gradient descent in blue, and from top to bottom is more and more accurate estimations of the loss function. And on the right, in the red box, we have the evolutionary algorithm. right, with more and more exact estimation of the loss function. And we see this, now we see like a different character of the optimizers. And now it's not just data, like how good can we deal with, but now it's actually character, like understanding what's going on. Because the stochastic gradient estimation with noise is pretty noisy. It goes like in many directions, but with more and more exact loss estimation, the gradient actually becomes more deterministic, right? And so everything you have here now is kind of the artifact of the stochastic gradient and not any more of the noise, right? But it's more one-dimensional. You can see this in the x-axis, which comes directly with ORQVIZ also, which tells you how much of the variance of the points is explained. And from top to bottom, it actually increases, right? It becomes more one-dimensional. But the evolutionary algorithm, even with exact estimation, it's not a gradient optimizer, right? So it's not deterministic. It's actually like genetically kind of figuring out many possible directions kind of, and testing if that lead to good solutions, right? So this is like, and then you can measure with PCA scan the underlying loss landscape. Now, of course, this is an approximation because for like if you see already here, only 40% and here 30% of the variance is explained in these two directions, but still in total it's like 70+%. And so the loss landscape, while it's not exactly what the trajectory is going, it's kind of representative for it. And we see roughly that these fall into different minima altogether, whereas the gradients fall in roughly the same minima, but it can't figure out exactly the perfect solution, as you can see here, right? So these are supplementary to each other. And if we only wanted to study now what's the effect on finite measurement on the loss landscape rather than on the optimizers, right? We can also do that. We can do scans with kind of the, right? So this is for VQE on hydrogen, what we just saw, but now with 4 qubits, and this other classic, like this generative model, which has a logarithmic loss function, right? And just for this difference between estimating the energy of a Hamiltonian and having kind of loss function as a logarithm systematically changes what noise does essentially on the landscape. Because on the energy estimation, the exact landscape is, right, so the median landscape with finite shots is exactly the same as exact landscape. Now, this is expected because the estimation of an observable with finite measurements is unbiased. The more measurements you take actually decreases the variance, but it's unbiased, right? So the median will go towards the exact. But if you have a logarithm in there and you undersample your expectations, it actually increases, right? It actually has a bias upwards. So if you can't extract back the exact landscape from a bunch of averages having finite measurements. Right? And so we see this even more if we then plot the 25th and 27th as 25th and 75th percentile errors of the median to the exact landscape. So here blue means that it's like negatively deviated, and red means it's positively deviated from the exact, right? And so in the VQE case, it's symmetric. It's not homogeneous, which is like already answering the next question you might have. Well, is the error introduced by finite measurements always the same? Could you just like model a kind of an epsilon sheet around the landscape and say, that, well, that's our width? Well, no, it's actually not symmetric. It's actually symmetric, but not homogeneous. And you see this instantly. But in the classic, in this like logarithmic loss function, even the low percentiles are just like way higher than the exact, like the exact loss estimation should be. So this is like studying a phenomenon being finite sampling, what happens with a loss landscape with finite samples, studying phenomenon through the lens of visualization. And here ORQVIZ was like super helpful. Like, okay, everything in this paper is generated ORQVIZ, but of course we do a lot of manual work figuring out what to scan. But keep in mind, all of these directions are like these 2D planes are spanned by the same directions, right? So I just have to kind of reevaluate the same grid of parameters, but now on a different function. Because here the function is the perfect estimation. Here, the function is the noisy estimation. Here, the function is kind of the right. So the difference between those in the negative and the positive sets. So it's super valuable for this exact case to fix the direction vectors that reevaluate different functions. And that's kind of natively super easy to do with ORQVIZ. And yeah, then you can do more and more fancy stuff. But I think once you conclude kind of, so from the scientific perspective, I really believe that people should use visualization. Now, we offer ORQVIZ open source, free to use for everyone. And we hope that people like it and they use it. But from a, like as kind of scientists, people really should do this. And like it will just improve our understanding very likely. It's just another tool to tackle the same research questions. And you can find the code here, as we have seen, and our papers seen here. And on the kind of community and software aspect, people, like, please feel free to use it. Feel free to contribute to improve our code. If you find bugs, if you find features that you would like, please reach out. If you have very nice plots that you would just want to show us, want to share with the community, this is like beautiful, please let us know. We hope you enjoy our work, and we hope that you actually find it useful for your own research if you do research.
And if you don't find it useful, also tell us, because we would like to know why it's like not useful for you. Which is like negative feedback is also definitely welcome. Mm-hmm. But we hope that won't be the case. Thank you very much for listening.
Okay, great. Thanks, Michał. Thanks, Manuel, for a great presentation. So for sure, we'll ask our participants for a feedback. There is, I think there is a clap from Piotr. I thought that maybe Piotr would like to ask a question. Piotr?
No, I just was appreciating the very interesting talk. I'm hesitating to say that, maybe it's futile, because obviously we are visualizing and you are visualizing so large dimensional spaces that it might not be very useful, but nevertheless it's nice, and I hope that might be useful, but I'm still hesitant. But nevertheless, thank you.
It also already has been, but yeah, I know what you mean. It's not a standalone solution. You have to be familiar with what you can do with ORQVIZ, but then you have to like apply your actual experience, knowledge of the problem you're tackling.
Yeah, it's a very challenging task to try to approach, and of course that's interesting. I don't know, imagine that you have hundreds of parameters, hundreds of qubits. What you can do with that? That's very challenging, and I don't know how to.
Actually, I think that the problem is, like, if you have a lot of qubits and the actually cost function evaluation takes a long time, this is like a big issue. But like I feel there is like not that much difference if you are dealing with 10 parameters or like 100 parameters, because that's already kind of beyond of like visualization. Like you always have to project it to like 2D. So it's confusing to, like for me at least, it's as confusing to think about 10-dimensional spaces as about like 100-dimensional spaces. So yeah, there are like more risk that the information will be lost in the projection for more dimensions. But I think like we did it for, I don't know, like
yeah, we had like, yeah. So this is like 14 dimensions,
yeah,
and this is like 40 dimensions. Yeah, right. So I think this one is like more probably, and then here we have QA away with 20 qubits, right? Kind of demonstrating a phenomenon, right? So it's like if you have a clear thing, we knew that this was very obvious to show, but this wasn't like obvious to everyone. That kind of, for example, parameter concentration in QA away looks like this. Like the parameter concentration means that the loss landscapes actually become the same essentially. And then here as a sign point, like we actually observe barren plateaus or something that looks like it as we like increase in the same like at the same position with the increased number of qubits, which is exactly what Aaron Plateau's would tell us, that the landscape becomes flatter and flatter away from standout features. That's what we see, away from standout features, like here, this kind of, this stuff here, it's becoming flatter and flatter. Right? It's not as, it doesn't like it's not like a wonder, like it's not a miracle, but it's a tool. And if you apply a tool just like any other tool, it will help you very likely.
Yeah, obviously, and these images are very beautiful, as in quantum information theory we can generate. And yeah, at least it is a didactic tool, which is for sure that is useful for.
At least, yes.
At least, yes, of course. I'm just hesitating that in research it might not be enough, but for explaining to others what's going on, amazing, of course.
Well, it's definitely not enough to explain it. So I'm very certain that it has its niches where it would be very hard to approach it otherwise. But obviously, like, this is supplementary to theoretical work, supplementary to raw numerical analysis. It's another tool. Yeah.
Come on. Like, weeks of compute can save you hours of doing theory. So
yeah.
And what about 3D visualization? Do you have any?
What about what? Sorry.
3D volumetric, for example, visualization.
Oh yeah. Yeah. So so we have a function that plots like 2D as 3D, which is this here, but we don't currently have higher dimensional scans than 2D. Right. So of course, the data can be aggregated in like higher dimensional tensor, but it's a matter of like how you would actually, like, would it be useful for visualization? I'm not quite sure, but if you have a use case where you actually would like to, like if it would actually help you and like to have a higher dimensional tensor of like 3D, 4D, 5D scan, let us know what you would do with that. Maybe we can implement.
I don't know, but actually, if you use opacity of a voxel as and color as a point of information,
then you can do 3D parameters.
Yeah, then you can have 3D parameter space, which is difficult to observe, but nevertheless allows you to have some insight about.
And it's even more expensive to compute, right? You have to say that's another kind of dimension that you're multiplying your like resolution with.
Yeah, of course.
So yeah.
All right.
Thank you.
Thanks, Piotr, for the discussion, for questions, and thanks, Manuel, Michał, for your answers. Do we have any more questions? I don't see more questions on our chat. The number of people has also dropped. So I think we can finish the presentation. So Manuel, Michał, thanks once again. Just before we finish, I would like to share my slides just to announce our next meetings. Okay. Yeah, and and as I said, we'll also send you a feedback form to ask for your opinion about this event. So the next event organized by Quantum AI Foundation and our Warsaw Quantum Computing Group will be, in fact, a joint event organized with Washington Quantum Computing Meetup. It will be on 4th of December, and it will be about building quantum computing ecosystem in Argentina, in fact, but the next Warsaw Quantum Computing Group meetup will be in January. We are also considering organizing one meetup in December. We'll see. It's still possible, but not certain, so we cannot promise. But it's almost certain that there will be a lecture on 10th of January given by Antal Chava from Xanadu, and the same will be about using PandaLane for quantum differentiable programming. And so that's the plan. At least it's possible that the title will change. Yeah, we would like to thank once again our strategic partners, Narto and Cogit, and our honorary partners for supporting us There are some new messages on the chat. No, these are just thanks from Manuel. Thanks from Manish. So it looks that our participants really enjoyed the lecture. So yeah, as I said, the recording will be later available on our YouTube channel. I now stop recording.